Hello everyone, I am Jomi Wu and I'm gonna record the homework solution for question number 1 in homework 10 for the course probability and stochastic processes. So in this question, it asks us to collect the definitions and simple properties for the following stochastic processes. There are 7 of them. The first is Poisson process, second is Poisson increments, the third is Poisson impulses, and fourth is semi-random telegraph signal, and fifth is random telegraph signal, and sixth is random walk, and seventh is Winner's process. So I wrote the first two in late text form. So let's say it's right here. So for the first, Poisson process is defined as following. So a Poisson process is defined by the following properties. And the first one is the number n t1, t2 of points ti in a interval t1, t2 of length t equals to t2 minus t1 is a Poisson random variable with parameter lambda t. So the equations looks exactly like this. So the second property is if the interval t1, t2, and t3, t4 are non-overlapping, then the random variable n t1, t2, and t3, t4 are independent. And the third property is at a time moment t, there is no more than one Poisson point. And using the point ti, we form the stochastic process xt equals to n 0t. So for Poisson processes, first order probability methods, it looks like this. Is p the probability of x equals to k equals to lambda to the power of k times t to the power of k and e to the power of negative lambda times t divided by the factorial of k. So its mean is lambda t, and its autocorrelation is lambda squared times t1 plus lambda times the minimum value of t1 and t2. And its autocovariance is lambda squared t1, t2 plus lambda times the minimum value of t1, t2 minus lambda t1 times lambda t2, which will be equal to lambda times the minimum of t1, t2. So the explanation of my understanding of Poisson processes is the Poisson processes mean lambda t is a linear function of time. So it makes sense to us because more buses are anticipated to arrive the longer we wait. So there is a term in an autocorrelation form function. So minimum value of t1, t2, which result from the independent increment properties I mentioned earlier. So for the second stochastic processes, it's called Poisson increment process. So its definition looks like this. So it defined as yt equals to xt plus epsilon minus xt divided by epsilon. So where xt is the Poisson process. So its first order probability methods is lambda times epsilon to the power of n times e to the power of negative lambda times Poisson divided by the factorial of n. And the mean of this process is lambda. And its autocorrelation function and the autocovariance function looks alike. So its autocorrelation function is lambda squared when the absolute value of t1 minus t2 larger than epsilon, and it will be equals to lambda squared plus lambda divided by epsilon plus lambda times the absolute value of t1 minus t2 divided by epsilon squared at a situation when the absolute value of t1 minus t2 is less than epsilon. So the auto covariance function is also divided by these two situations. The first situation, it will be equal to 0. And the second situation, it will be equal to lambda divided by epsilon minus lambda times the absolute value of t1 minus t2 divided by epsilon square. So the explanation of my understanding on this processes is we can see that the lambda divided by epsilon, and so its autocovariance is a triangle with area lambda when absolute value of t1 minus t2 is less than epsilon, and the triangle transforms into an impulse with area lambda when epsilon reaches 0. So for the following stochastic processes, I wrote it down. So for the third stochastic processes, it is called the point impulse process, and it is defined as following. So zt is equals to dxt divided by dt, where xt is Poisson processes, and its graph looks like this. So its probability mass is no definition, but its mean is lambda. Its autocovariance is lambda squared plus lambda times theta t1 minus t2, and its autocovariance is lambda times theta t1 minus t2. So my understanding on this process is the process zt minus lambda, which is a point impulse process. So has no mean, and its autocorrelation rt1 t2 is equals to lambda times theta t1 t2. So I'm sorry, it's not the point impulse process. It's the white noise of this process. So it's defined as the output of a linear time environment system with the impulse response ht and input is an Poisson impulse process. So for the fourth one, so its name is semi-random telegraph signal. So its definition is defined as xt is defined based on Poisson points and a number n t1 t2 of the points ti in an interval t1 t2 of length t equals to t2 minus t1 is a Poisson random variable with parameter lambda t. So the equation is looked like this. I'm not gonna read this. So xt will be equal to 1 when k is even, and it will be equal to negative 1 when k is odd. So its first order probability method is pxt equals to 1. It will be equal to the e of. So it's basically the same as its definition. So except its divider changed to 2. And the probability xt equals to negative 1 will look basically same, except the plus is changed to negative to minus. So it's mean of this the mean of semi-random telegraph signal is e to the power of negative 2 times lambda times t, and its autocorrelation is e to the power of negative 2 lambda t1 t2's absolute value. So and its autocovariance is e to the power of negative 2 lambda t1 t2's absolute value minus e to the power of negative 2 times lambda t1 plus t2's absolute value. So my understanding of this function is the probability of xt equals to 1 is a little bit higher than 0.5, since we start calculating from minus 1, positive. So for the fifth process, it is called a random telegraph signal. So it's defined as yt equals to alpha xt. So the probability of 1 and negative 1 will all be equal to 0, 0.5. So where xt is semi-random telegraph signal, So for this process, its first order probability methods is are both 0.5, and its mean is 0, and its autocorrelation and autocovariance is exactly the same. So my understanding of this process is the reason that we can use since the random telegraph signal has the property of the probability of 1 and -1 will all be 0.5. So we can say that the YT maybe can be defined as strict sense stationary, which is also known as SSS. So for the sixth process is called a random walk, and it's defined as a Toll-Sphere. We Toll-Sphere coin n times k, and k is the number of heads in n tosses. So we can say that xnt is equals to xs minus n minus k times s, which will be equal to 2k minus n times s. So its probability method is like this. I'm not gonna read this. So its mean is 0, and its autocorrelation and autocovariance is exactly the same as shown here. So my understanding of this process is if n tends to be infinity, the probability masses will be look like the Gaussian density. So for the last one process is called winners. I don't know how to read this process. So it's defined as the equation right here, where xt is the random walk. So for this process, its first order density function is look like this, and its mean is 0. And its autocorrelation and autocovariance is exactly the same. They are both the minimum value of T1 and T2 times the alpha. So my understanding of this process is continuous path. And thanks for watching.